In this example, we will discuss a combined loading problem. So we have a crankshaft that is loaded in three directions. So in the X direction, the Y, and the Z. And this setup basically creates stresses of different kinds in the rod AB. So we're interested in the stress state of rod AB, and the idea is to isolate the different types of stresses that occur and understand the magnitudes of these, which is negligible in comparison to the others, and then develop the stress state of the most critical point on that rod, and understand what are the principal stresses and maximum shear stress using the Morse circle. So this should be sort of a review from 306, but I'll break some things down really quick and then jump right into the problem and solve for the stresses that are required. So again, it's a cantilevered bar or a crankshaft made from ductile material, statically loaded in three directions, X, Y, and Z. And we're expected to analyze the stress situation in the rod AB by obtaining the following information. So the first thing we need to do is determine the precise location of the critical stress element. Once we understand where the critical stress element is located, we can combine normal stresses, shear stresses, and draw a critical stress element that can later be used in developing a Morse circle that's going to give us the principal stresses and the maximum shear stress. So what I'm going to do first is just briefly talk about the stresses and the way I approach the problem. So I like to break down a combined loading problem into its separate components and the different stresses like axial, bending, and then the respective shear stresses, and then solve each one of them individually and then combine them at the end. So first, okay, so as you know, we have two kinds of stresses, normal stresses and shear stresses. And under normal stresses, we have axial and we have bending. And under shear stresses, we have transverse shear and we have torsion. Again, this is just a sort of a recap from 306 or 303 EMA if you took it with that department. Um, so again, normal stresses are induced when the load is perpendicular to the cross-sectional area. And shear stresses arise when the load is parallel to the cross-sectional area. So if I were to make a rough schematic, I would have probably something looks like this. And when I apply a load, it elongates. And here the area of the beam goes into the page. Similarly, in shear stresses, the load is applied. So let's say we have a beam and apply a load here. And you need a counteracting load to keep it in static equilibrium, like I have in the normal stresses. And what ends up happening is, you could say, it drops down and is offset. So this load right here is parallel to the cross-sectional area. So what we can do is now figure out from all these forces what each force gives rise to. So for example, does Fx have create both axial stresses and bending stresses in AB, or just shear or just torsion? So that's kind of the next step. So let's look at axial first. So what I'm going to do is tackle axial torsion transverse shear, and bending. And now the reason I do that is after doing these kind of problems for the last 2 years, I've realized that it's bending is kind of the most crucial in probably this entire course, and then torsion, then axial, and then transverse shear. So I'd like to check off those, or rather complete the easy ones first. Not only will that give me, a good head start on the problem, but also it's like easy partial credit. So, and it's pretty obvious, like axial and transverse shear and even torsion, those are like kind of really easy to observe just from the problem, but bending can be a little tricky because if you've watched the countershaft video, you kind of sometimes have bending in two planes and then you have to take the sum of squares, and that can make things a little bit complicated. We will cover that in this problem. And in my opinion, this problem is actually pretty good, as in it covers all the basics that you need coming into this class, and it's as exhaustive a review of 306 that you need to do well in 342. So let's look at axial loads first, right? And again, axial loads is just a normal stress, and you have either tension or compression. And I'd like to note axial stress as sigma A. Again, I use sigma for all normal stresses and tau for all shear stresses. So sigma A, and if you remember, it's the load divided by the cross-sectional area. So let's look at the diagram and see what forces are creating an axial load. So Fy, and we're only concerned with the rod AB. We don't care about BC or the little pin at the end or the handle with the crankshaft. So what Fy basically does is if I move this to a point where I'm only interested for an AB, Fx kind of pulls it, it elongates AB in the x direction this way, right? So Fx kind of creates, it pulls AB in tension, and there should be an axial stress developed due to Fx. Again, you have to move Fx 5 inches towards the x-axis to see how it kind of affects AB. Now Fy just pushes up this way, so it doesn't really elongate or compress AB in the axial direction. So Fy is not an axial load, and Fc as well pushes it in the z direction, which again it doesn't elongate or compress it, which means it's not an axial load. So the only axial stress in this problem comes from Fx. So the load we have is Fx, and the cross-sectional area is that of a round beam. So that's pi d square over 4. So that's 4 times, and then Fx is given to us as positive 75 pounds of force. So that's 4 times 75 over pi, and the diameter, and now we need to substitute the diameter of the rod AB, which is 1 inch. So that's 1 square, and that gives us 95.5, and the units are going to be pounds of force divided by inch square, or in other words, 95.5 psi, right? So this is sigma A. And the other thing you need to do is figure out what the direction is. Is it positive or negative? So in this case, f of x is drawn to be in the positive x, and you can also tell from observation that f of x is going to stretch AB, which means it's in tension, which means it's a positive stress. So this is going to be positive 95.5 because it's in tension. And this is important because when we combine stresses later, we need to understand if two different loads, normal stresses are in tension compression or tension and tension, so then we'll add them or subtract them at a certain point. That'll give us an idea of what the critical stress element actually is. Because if one force gives rise to tension and then the other one gives rise to compression, then they kind of cancel out and don't have that drastic of effect as you would have tension and tension superimposed on top of each other. Okay, so this is for axial. The next thing I'm going to look at is torsion. And torsion is basically, again, it's a shear stress. and it's whatever causes rotation about the axial axis. So what I mean is along the length, whatever axis you have, so in this case we have the x-axis, whatever causes rotation or a twisting motion, or maybe like a torque. And we had to calculate that stress. If you remember from 306, it would be tau. For torsion, I use tau T, and then I use tau S for transverse shear. So tau T is equal to T rho over J, where T is the torque, rho is the distance from the center of the cross section, and J is the polar moment of inertia of the beam. So in this is for a rounded shaft, and so we need to find the torque that is causing the torsion, and we need to see if we have torsion in the beam to begin with. Now, if we look at x, fx, it doesn't really cause a rotational motion. It just bends the beam this way, but it doesn't twist or doesn't rotate the beam. So you could think of, so a crankshaft is basically you cranking it, right? And if you apply a force that looks like fx, you won't really accomplish what you're trying to do. Similarly, if you apply a force that looks like fc, you won't accomplish what you want to do. But if you try fy and you pull it, in this case it's pointing upwards, but it's negative, so you're technically rotating it clockwise, right? So Fy here is negative 200, which means effectively you're pushing it downwards. And if I look from, I'm going to erase this. If I look from the positive x towards the origin, this means that it's rotating clockwise. So Fy is the only force here that's causing rotation of the beam or of the shaft. And so And then the torque, we need to know what the moment arm is for that rotation. And that's going to be 5 inches, right? Because you're applying that force 5 inches away from the shaft, which would cause it to rotate. So that's going to be, let me separate this. So the torque is equal to Fy times L, which is the torque arm, I suppose. And we'll say that's 200. So you might wonder if you have to use minus 200, 200. At least for the purposes of this class, I wouldn't worry about signs when it comes to shear stresses. Just for the sake of this class, because what happens is if you try to take the signs into consideration, you'll be working with tensors and that kind of makes the problem really complicated. And from a design perspective, at least, from a higher level, you don't really need to know the signs of the shear stress, because especially when you're dealing with drive shafts that are really long, the shear stress is the transfer shear isn't really that important, so you don't need to add or subtract it. But if you want to go ahead, I think Dress might mention something about it in the lecture. You can take a look at it if you're worried, or if you want to know more about the science. Or again, you can stop by office hours and we can discuss it more. All right, so again, for shear stress, I'm not going to worry about the sign, but for axial, I will. So we have Fy, which is 200 pounds, and the moment arm is 5 inches. So the torque is going to be 1,000 pound-inches. Again, like I did in the countershaft, I'm going to work the entire problem in pounds of force and inches. Last time I did pounds of force and feet. This time I'm going to do pounds of force and inches, and maybe PSI or KSI, depending on if the value is really large. Okay, so that gives us the torque, right? And now we have rho and J. So it's pretty obvious that when you twist, so from this equation, you can say that as I go from the center of the shaft outwards, the shear stress due to torsion increases, right? Because this is rho effectively, and rho can be any point. It could be halfway through the cross section of the shaft or all the way to the outer surface. So this value will be maximized at the surface. So torsion, or the shear stress due to torsion, is maximum on the surface, and this torsion will be felt throughout the entire cross section of the shaft. So it doesn't matter exactly where on the shaft, but on the outer surface. So what I'm going to do is simplify this and substitute for rho, I would substitute d over 2, which is the radius, so the diameter over 2, and the polar moment of inertia for a rod is pi over 32 d to the fourth. And simplifying that, the d cancels from the top, bring this to the third power, and then the 2 would convert this to a 16, and simplifying that will give me 16t over pi d cubed. So this equation right here is the shear stress due to torsion on the surface of a solid round shaft. And this is actually a very useful equation to use. We will use this a lot to use in your project. You use it in a lot of other problems later. So I would remember this. So important to remember. You can derive it. It's also in your textbook, but it's important to remember. That we're not wasting precious time in the exam or the quiz fishing for this equation or deriving it. Okay, so now that I know T, I know D, I can figure out what the shear stress due to torsion is, and that is tau T is equal to 16 times 1000. Again, this was in pound inches, divided by pi over d cube, and the diameter of the rod AB is 1 inch, right? And this is inch cube, so this would become inch square, and we're left with 5093 psi, or 5.09 ksi. So now we have torsion. So let's go and evaluate the transverse shear next. Transverse. Now for transverse shear, if you read already, there is a statement that says transverse shear may only be neglected if you can justify this decision. Now, when I'm combining stresses later, right? I'll combine torsion and the transverse shear, and I would combine axial and bending. We need to see how big each value is with respect to the other. So for example, if the transverse shear is a lot smaller than the torsion value, like multiple orders, then I can just completely ignore it. At least for the purpose of the design, because later on in the semester, when we're evaluating safety factors, you'll see that by dropping the transverse shear, you would probably change your safety factor by 0.001. So at least for design purposes, it's easier to drop transverse shear, but nevertheless, if you want to, then tau s is equal to VQ over IT. And a quick refresher, if this is your rounded beam and you have a shear force that acts in this direction, again, it has to be parallel to the cross-sectional area, right? And you're interested in the shear stress at this point, you would draw a line across, and the shaded area here is going to be Q, right? Which means that, and V again is the shear, I is the inertia, T is the thickness. But what this means is if I am looking at an element that's sitting on top of the shaft, Q would be equal to 0. And if Q is equal to 0, it means that tau S is equal to 0 at the top. And Ts will be the max at this point right here, right? Because the area here is going to be the largest. So Q will be the largest, which means the shear stress will be the largest, and none of the other values will change. And if you want to evaluate that for a solid round beam, it would be 4V over 3A, where V is the shear force and A is diameter or the cross-sectional area of the shaft. Now, if your let's say your shaft is actually pretty long, so that means that the L over D ratio, which means the length of the shaft versus the diameter of the shaft is a lot higher, then let's look at what tau S looks like in comparison to tau T. So tau T was 16 times F times L over pi D cube, and tau S is 4V over 3A, right? And A is basically pi D to the fourth, so pi D squared, so I'm just going to say pi D squared. There's another 4 up here, so that would become 16 times V, right? So if I were to compare these two and I have a really high L over D ratio, it means L is large and D is small. Let's cancel out the 16, cancel out the pi, we'll have a 3 in there, and you have D, right? So L by itself, if it's high enough, is going to increase tau a lot, right? And it's not going to change tau S. And also, if D is really small, the denominator is going to drop here a lot more than it will drop in tau S, and will also increase tau T. So in this case, we have a 1-inch diameter versus a 6-inch length. I feel, so this is a ratio of 6, and that's a pretty high ratio. And you can make the assumption here that tau S, or the transverse shear, can be ignored. Now, you don't have to, like in exams and stuff, if you're going to ignore it, don't you don't need to show the equations and stuff. You can just say a very high L over D ratio means that the transfer shear is negligible, or it, it's small enough to be ignored. So it can be ignored, and you can also do this in your project. And in this class, you'll find yourself ignoring transfer shear for the most part. Project. But if you want to go ahead, you can calculate tau S, right, using this equation right here. You can figure out what forces here causes shear, transfer shear. So in our case, we would have Fy, right, because it shears in this direction, and Fc because it shears in this direction. And then you can substitute both those values and see what order of the values you will get. But this argument here, that a high L over D ratio means I can ignore transfer shear, it's well and good. And again, if you find yourself running out of time, you can basically not lose any points if you don't even evaluate transfer shear and just write the statement. I've never seen anyone get points taken off because they didn't calculate transfer shear. But make sure that you add the line where you state clearly the assumption that a very high length over diameter ratio allows me to ignore transfer shear, not because transfer shear is small in magnitude, but because it is small in comparison to the torsion. All right, cool. And then finally, we have the bending moment. Now this one's going to be tricky and it's going to be fairly long. So I would maybe take a break right now, and you don't have to understand the previous stuff to understand this, but and maybe come back in like 5 minutes with some fresh eyes, because it's going to be there's going to be a little bit of vector here, and some squares. So, and trying to visualize this stuff in 3D space can be a little tricky sometimes. But if you think you're good and everything I did before was pretty straightforward and easy, then let's continue. All right. So bending. What does bending mean? Well, what I've noticed with a lot of students is, let's say you have a shaft here, right? And then you have a handle, and then you rotate it. They, this is torsion. Like I said, Fy causes torsion in the beam. This is not bending. Okay. But if I have, let's say I'm looking at the crankshaft from the top, right? I see this. So this is going to be my z-axis. This is going to be my x-axis. If I apply a load such that there's going to be so let's say I apply a load this way, right? Such that one point on the shaft is in compression now, and the other side of the shaft is in tension, right? The exact opposite side of the shaft is in tension. We classify this as bending. So don't be confused. If bending basically happens when opposite sides of the shafts are in compression and tension respectively. Okay, and from 306 again, to calculate the bending stress, it would be minus mc over I, right? Where m is the moment that causes the bending, and in this case, the moment would be, let's say, the moment or the stress at this point right here. Wait, the point right here, the moment would be this force multiplied by this length over here, right? Because that's the perpendicular distance from that element or that stress element to the force. And for a rounded shaft again, we can make some assumptions, and it's also pretty evident that the maximum stress is going to occur at the outer surface, because in this case here, it would be in compression here, but an element over here would be a little bit less compressed. An element here would be probably neutral with no stresses at all. And then somewhere down here would be even more extended, right? So your elements will be mostly compressed or in tension at its maximum value on the surface of the beam, right? And it's important to note, again, like I showed here, if you have a beam here, right, and this is in compression, right, let me use a different color. This is in compression, this is in tension. That means that the force came in from this direction right here. Convince yourself of that the force coming in this direction is going to bend even though the force is parallel to the cross-sectional area, it actually bends. Wait, sorry. It's going to come in from, well, okay. Oh, no. I drew it the wrong way. So not the cross-section area, but rather the length. Sorry about that. This is the length of your shaft. Yeah, this is going to be whatever length you have, A or till B. You're going to have something that's compressed this way, right? Let's say it originally looked something like this. And on the other side, it originally looked something like this. And now it looks like this, right? This happens because you have a force that bends it this way, right? And that's basically, this is the moment M. So and it's going to be maximum here at the top and the bottom, and it's going to be 0 along the neutral axis. Okay, because here it's going to be technically in both, like we're going to assume it's a very, very small element, so it's going to be like a little bit in compression, a little bit in tension, both will cancel out, the stress is effectively 0. So let me write this down here. So sigma B is equal to negative mc over I. And for a rounded shaft, right, and we said that this is going to be maximum at the surface. So it's going to be, and c again is the distance from the center of the cross section. So it's going to be minus m times c, where c is d over 2. And I, in this case, is the area moment of inertia, and that's pi over 64, because if you remember, I is equal to j over 2 d to the fourth. These cancel, make it the 3. This would make it 32. And what you're left with is sigma b is equal to 32m over pi d cubed. Now I didn't put the sign in here because what I like to do instead is observe which from the force that I have, what is in tension, what is in compression, and then provide it a sign accordingly. So you can do that. And that's kind of what I recommend, because after a point it becomes difficult to realize what exactly is happening. But generally, let's say, for example, in this case, the moment or the force is pointing upwards, right? So generally, students will say, okay, because it's pointing upwards and this is positive, I'm going to say this is going to be in tension because it's a positive value, because it's on top, right? It's the positive y. But actually, it's in compression. That's where that negative sign comes from in the beginning. So evaluate the magnitude, and then by observation, you can tell what's in compression, what is in tension. If you want to understand mathematically, I would suggest reaching out to Dress because he'd probably be able to explain that a little better. Okay, and again, this is the bending stress, which is the maximum at outer surface of a solid round shaft. All right, so now we need to evaluate the bending stress, but for that we need to know the moment. And now if you see it, as if you've already watched the countershaft video, you'll realize that from these right here, from the forces we're applying right here, let me erase all of this, you have Fz, right, that bends AB this way, right, about the y-axis, right? Fx also bends it about the y-axis, and Fy bends it about the z-axis. So if I draw this down here, okay, so let's say I'm looking at my rod AB from the top view. So this makes the axis Z and X here, and by the, I don't remember the right hand rule. Yeah, Y points out, upwards or out of the page. You have, this is your original shaft, right? And because of, let's look at Fx first, right? Which is basically coming out this way. It's going to cause the beam to bend this way, right? And again, we have compression, we have tension, that means we have bending. And this is going to be bending about the y-axis, right? Because it's pointing out. And by using your right hand rule, like curl your fingers, you point, and it's rotating clockwise with y pointing out of the page. So y has to point, for y pointing out of the page, positive moment is for y pointing out, right? If y is pointing out, this is conventionally, right, anti-clockwise is considered positive, but this is rotating counterclockwise. So this is the moment. F of x, fx is causing a moment about y, which is negative, right? Then we have, similarly, we have again the xz coordinate, AB, and A is up here, B is down here, A, B. Z is coming in this way, right? So it's also going to bend the same way. Again, FC causes a counterclockwise, oh, sorry, this is clockwise. Again, causes a clockwise motion. So again, moment about y and is negative because y is pointing out of the page. And then finally, we have our y-x coordinate. This is our shaft. And Fy is causing it to bend upwards, downwards actually, because it's negative 200, so it means it's pointing downwards. So our shaft looks like this. And this, if this is, so now we have z pointing out of the page, and if we use the right-hand rule with the counterclockwise motion is positive, if, well, if z is pointing out, this is considered positive, which is counterclockwise, but this is moving in the counterclockwise clockwise direction, so this is also negative. So moment about z due to Fy is also negative. So now what we can do is combine these two first, and then take the sum of squares in both the planes because we know what the y is, what the z is, and then we can solve for the moment. And again, you will have to find out what the resultant moment is on a given cross section before you calculate the stress. So what else do we need before we further? So we know the force, right? So this is Fx, and it's being applied at a moment arm, which is 5, right? This is being applied at a moment arm, which is 8, and this is also applied at a moment arm, which is 8. And this 8 comes from the 6 on the rod plus the 2 from the handle. And the same thing goes here with the second one. So this is 1, 2, 3. So now we have my is equal to, and both these moments will add because they're both negative. So it's going to be negative Fx times 5 minus Fc times 8. Fx we have, so I'm going to pull out the negative, it's going to be 75 times 5 plus, no, Fc is 100. Again, I pulled out the negative, so that's why it's a plus. I factored it out, times 8. And so my is equal to negative 1175 pounds of force, inches. And then the moment about z, again, these are vectors, right? So when I say moment about z, means it's rotating about z or rotating about y, not in the direction of z or in the direction of y. And yeah, minus Fy minus Fy times, is it negative? Just hold on a sec. Negative 200, z pointing out. Yep, that's negative. Yep. So negative Fy, but here I've treated Fy to already be pointing down. So this is simply just going to be the magnitude of Fy. Multiplied by the length, which is 8. So that's negative times the magnitude of negative 200 times 8. Right? Or you could say, okay, Fy I'm going to take as pointing upwards. And I'll just say, okay, this is Fy, and then I'll preserve the sign and then use it later and say, okay, it's just going to be Fy times 8, but Fy is actually negative 200 because I preserved the sign and then multiplied by 8. Either way works. So Mz is negative 1,600 pound-inches. So what that looks like basically is you have y pointing this way, z pointing this way, right? So you have negative 1,600 in the, or 1,600 in the negative z, and negative 1175 in the y. So your resultant moment is going to be in some direction. Let's say here, closer to the z-axis, so 1600 is larger, right? Offset by some angle. And this is going to be m total. So m total is just basically the sum of squares, which is equal to square root my square plus mz square, which is 1600 square plus 1175 square. So m total, or the resultant moment, is 1985 pound inches. So this value right here is 1985. Okay, and so wherever, so now that we have the shaft, right? Let's say the shaft is this way, right? We need to know where the maximum compression or tension occurs, right? It actually occurs offset from the z or the y-axis, and it's going to be at some angle. But what we have here is actually the moment vector, right? We have, so if the force is being applied in a certain direction, the moment is actually F cross product, the R. So what you need to know here is the critical shaft element is actually located 90 degrees from where the moment vector sits. So that's going to be somewhere here, but this is 90 degrees. So the critical section, again, the reason the bending moment dictates where the critical section is located is because torsion is applied throughout the entire cross section of the shaft, and so is the on the outer surface of the shaft, and so is the axial stress, which is applied on the entire cross section. That's why the moment dictates in this case where the critical section is. So critical section is plus or minus 90 degrees from moment vector. And we'll confirm that later. Right? So what is that angle here? So we need a reference point. So let's say I want to figure out what that angle is, and I'll say it's, okay, it could either be this angle here from the y, or this angle here, but both values are the same. So I'll just find phi and then figure out whether my critical location is at this point on the shaft or down here at this point of the shaft. So phi is equal to tan inverse 1175 over 1600, and that is equal to 36.3 degrees. And the bending stress is 32 times 1985 over pi times 1 cube, which is 20,220 psi, or 20.2 ksi. Okay, now we need to figure out whether this is going to be in this location here or this location here. And that comes down to which direction are the two normal stresses, which is the axial and the bending, superimposing. So we know that the axial is in tension and the bending stress is going to cause tension in one point and compression at one point. So how do we figure that out? So if we look at the diagram up here again, and if I were to draw, I'm just going to shrink this a little bit and draw it here. Right? So if I were to draw it this way, and y is, actually I can just use a diagram here. Right? If I look at the first case here, where because of the moment caused by fx, you see that the elements in the positive z are in compression, right? So this is your x-axis right here, everything in the positive Z is going to be in compression, and everything in the negative Z is going to be in tension, right? So, and we know that we're going to add those in tension and subtract those in compression. So the axial stress is in tension, so we know that we're only interested in the points that are in tension. So based on Fx, everything here is in tension, right? In the in the negative Z. If we look at case 2, same thing happens. Positive Z values are in compression, negative Z values are in tension. So again, tension here due to Fx and Fc. And if we look at, so now we know it's going to be in either this quadrant or this quadrant. And if we look at the bending stress due to Fy, we have it pointing downwards, which means that in the negative y, we have everything in compression, and in the positive y, we have everything in tension. So positive y, tension due to Fy. So based on that, it's going to be in the first quadrant, which means that not this, but this is our critical location. So phi, or the stress element, is located 36.3 degrees clockwise from the positive y. So this is the answer to the first part. Okay. All right. So now we've determined all the 4 kinds of stresses that we needed. We ignore transfer shear, of course, and we know exactly where the critical stress element is located. Now it's time to combine these stresses, right? So we can combine the normal stresses, and both these normal stresses are acting in the x direction. Because if you look up here, right, this element here is stretching or compressing, is stretching or compressing in the z direction, right? You have your z-axis right here. So it's compressing or elongating in the x. Similarly over here, it's stretching in the x or compressing in the x, and even over here, it's compressing and stretching in the x. So effectively, it's a normal stress, right, where the force is perpendicular to the compression or elongation is perpendicular to the cross-sectional area. The normal stresses are in the x, and so was the axial stress. So we can directly add those. So sigma x is equal to sigma A plus sigma B, which is 20,220 psi, 20 plus 95.5. Now these two are values of different orders. The bending stress is actually a lot higher than the shear stress, than the axial stress. But however, the reason we are using this value, or we actually kept this value without disregarding it is because we needed to figure out whether our critical section is going to be here on this side or on this side. And now that we know its intention, it's very likely, or rather, there's a good chance, there's a slight chance rather, that it's going to fail 36.3 degrees clockwise from the positive y rather than from the negative y. So that's kind of why we carry on the value and we calculate it, so there's no harm in adding it. If you find yourself running out of time, you can just make a quick ballpark estimate and say that, okay, I'm going to drop 95.5 because it literally doesn't affect my results. That's a fair assumption, and we'll take it. So sigma x is 20,000 plus 95, which is 20.3 KSI. And if we combine the shear stresses, but we ignored the transverse shear, we're only worried about tau, which is tau t, and that's 5.09 KSI. So that checks out part A, and we determine the magnitudes and directions. And so when it says sketch the critical stress element, all it's asking you is, in that given configuration, what do the stresses look like, right? So you have a stress element, and let's say this is your X, and this is your Y, right? You have sigma X in both directions, right? Because it has to be a critical element that's in equilibrium, and tau, or the shear, is drawn in this fashion, where both arrows should point to the same corner. And tau here is 5.09 KSI, and sigma x is 20.3 KSI. And we call this uniaxial shear loading, right? Biaxial means there wouldn't be any shear, but there would be a sigma x and a sigma y. And the reason we have sigma y here is because there is no axial or bending stress in the y direction, which means that your elements don't compress or elongate in the y-axis. Okay, so that is part B. And finally, part C, we need to figure out the principal stresses and maximum shear stress. Now, the stress we calculate here is not the maximum shear stress. Anytime you see the words maximum shear stress, you need to understand that you have to use Morse circle. Principal stresses, definitely Morse circle. Now, there are two approaches to using the Morse circle, right? You can use the equations that are available to you that are derived from basically the equation of a circle, or you can draw a circle. I personally like to draw the Morse circle because it helps me visualize the stresses, and that's kind of what we also ask in most of the exams or quizzes is, please draw a 3D or a 2D Morse circle to show your results. Because if you use the equation and you make a sign mistake or something computation in the calculator, it's a straight zero because there's really no work in you. All you did was copy paste an equation from the textbook. But if you draw the circle, we know that you understand, how exactly to transform stresses using a circle. So now using this element, I'm going to draw a circle, or the Morse circle. And I'm going to draw the 3D Morse circle. And I would suggest drawing the 3D Morse circle at all times, especially when, let's say you have something that looks like this, which is not crossing the shear axis, because you'll know that there's going to be an extra circle here, followed by a larger circle that completes it, and this would be your tau max. So I would always draw a 3D Morse circle just to be safe, because there are going to be other planes, or rather maximum stress that doesn't show up in the current configuration, and you need to complete the entire Morse circle to find that one. So if I were to draw my Morse circle, right, traditionally you would, so we have sigma x as 20.3, and we have tau as 5.09. So this is sigma, this is tau. Your first, and sigma y is basically zero, right? Because you don't have any stress in there. So you're going to use sigma x and tau as your first coordinate, and then sigma y and tau as your second coordinate. So we have 20 and 5. Again, this is not to scale. So this is 20.3. Then this is 5, right? And this is going to be -5 and 0. And you can draw a line that joins these two, right? I did it the other way, where I drew the circle first and then I plotted the points. I kind of do that usually because by just looking at the numbers, I can tell what exactly this is going to look like. Is it going to cross the y-axis or not? is it more skewed towards the right hand side or the left hand side? But you can use the traditional way and plot the points first, join the dots, and then draw a circle around it. Now, whenever you draw a Moore circle, you have to label at least the principal stresses, the center of the circle, and the maximum shear stress. So your maximum shear stress is going to be here, right? And your center is going to be here. Sigma 2 is going to be here. Sigma 1 is going to be here. And if I were to draw a 3D Moore circle, I also need to realize that sigma z is equal to 0. So I'm going to have another stress state here. And that means that is going to be sigma 2, and this is going to be sigma 3. And if I were to, let me see. See if I can get this right. So this is your first circle, right? The other one, and then the smaller one, which looks like that. So this is basically your 3D Moore circle with three principal stresses, a tau max on the larger circle. Now, because the circle that you drew crosses the tau axis, that is going to be the largest circle you have. But in the case of this diagram here, which is especially characteristic of pressure vessels, you might have your circle only take up the right-hand side of the tau axis, and then you'll have to bring in that third stress and draw the bigger circle. So let's calculate the values now for tau max, sigma 1, sigma 2, and sigma 3. So first we need to know the properties of the circle. So we need to know that center, and we need to know what the radius is. And sigma 1 is basically the center plus the radius. Sigma 2 is 0, and sigma 3 is the center minus the radius. And the center is simply 20.3 minus 0 divided by 2, which is 10.15, and the radius is going to be the hypotenuse of this triangle right here. So this is also the radius, and the sum of squares is 20.3 minus c, the whole square, plus tau square, which is 5. I can write this as sigma x. So if I were to evaluate that, it would be 20.3 minus 10.15, the whole square, plus 5.09 squared. This again is 5.09, 5.09 here. So R is, or the radius of the circle is 11.35 KSI, KSI. So again, now I can compute sigma 1 and sigma 3. So sigma 1 is 10.15 plus 11.35. Sigma 1 is equal to 21.5 KSI. Sigma 2 is 0. Sigma 3 is 10.15 minus 11.35, which is negative 1.2 KSI. And tau max is equal to the radius, which is 11.35 KSI. So anytime you need to draw a Morse circle, I would suggest drawing a 3D Morse circle and